Let's begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, thank you for this class and this opportunity we have just to study your creation together. Just pray to be with us today. Help us to glorify you in what we do this day, Lord. In your name I pray. Amen. All right, so let us take a quick stroll down memory lane. Let's see here. So I told you the things at the start of last class. In particular, that's a quick list of what is important about R being a PID. Haha! Hooray! Now I have turned back 80% of test 2. All right. So then we talked about annihilators and orders. Remember we said that if n is a submodule of m, then any generator of the annihilator is called an order of n. The order of an element is the order of the submodule which it generates. We mentioned that the idea of the order was more like a group exponent and less like the order of a group. I told you that if we had two different orders, they were related by associate. In other words, there's multiplication by a unit in the ring, which takes you from one to the other. So we just glibly refer to any of these as the order, which is, of course, abusive language since there could be more than one, although sometimes not so much. For example, if we're working with a Z module, the order is two things because we have 2 units plus or minus 1. I mean, if we were working with something more exciting, we could have a bunch of orders, right? For example, working with a polynomial ring, then multiplication by any non-zero scalar of the order would be an order. All right, anyway, we also have this result. If m is the direct sum of a and b, then the order of m is the least common multiple of the order of a and the order of b. We actually worked through a good bit of that yesterday. Listen to me. Well, as you know, the weekend doesn't exist to us. All right. This is what I did at the very end of class. I talked about a cyclic module. It has annihilator, Langle, Langle, Wrangle, Wrangle, V. I'm sorry, Langle, Langle, V, Wrangle, Wrangle. And that has annihilator, Langle, alpha, Wrangle. And we define the tau map by multiplication that induces the isomorphism here on the quotient, which shows you that any cyclic R module is isomorphic to the quotient of a quotient module of a base ring. Let's see here. Any submodule cyclic, R module cyclic, and we had these super nice formulas relating the order of various things as they may or may not be relatively prime, right? So like this is, suppose you want to get another generator. You want another order for the cyclic submodule generated by V. Then if you can find a beta such that, and beta's in the ring, of course, such that the order of V and beta are relatively prime, then you'll generate the same cyclic submodule. So, all right. So, I also told you this last time. This is how we can compose. If we have relatively prime orders, we can compose the direct sum of them to get the Langle, Langle, sum, Wrangle, Wrangle of the orders. And vice versa, if we have the order as a product of pairwise relatively prime orders, then it follows you can decompose the Langle, Langle, V, Wrangle, Wrangle into the Langle, Langle sum of U1 through UN, Wrangle, Wrangle, as being, well, anyway, right here. Okay. Again, I will at some point soon provide you with a scan of Roman's linear algebra. My apologies about that. All right. So the next thing that Roman proves is that if you have a free module over a PID, then any submodule S of M is also free and the rank of S is less than or equal to the rank of M. Rank being the number of things in the basis over which S is free or over which M is free. And then theorem 6.6 says that if you have a free module of finite rank and if you have S as a spanning set with n things as a spanning set for M, then S is a basis for M. So that's pretty nice, right? Now, spanning is important. If you delete the term spanning there, it doesn't work. If you just have a set of n vectors, in a rank n free module, that doesn't do it. For example, the integers are a free module, rank 1. Take the set containing 2. Not a spanning set, right? The set containing 2 hits the even integers, right? And there's no way you can fix 2 and make it into a basis using integer stuff. So that little, don't miss that spanning set. In other words, it has to cover the whole stupid thing. And then here's a somewhat unfamiliar to me. I probably should do a problem in this. I probably should assign you a problem on your test 3 to explore this concept, because it's not quite native to my intuition just yet. Maybe I understand it, maybe I don't, I'm not sure. But if you have a free R module and you have a submodule, VK, right, and you have a basis for M, then you can take that basis and modify it by multiplying by appropriate non-zero constants in your ring to get a basis for the submodule. So that's, I'll be honest, I don't quite get that.
Doesn't the input say also that R1 divides R2 divides, or is that something else?
That's something else. But there may be a version of this theorem like that in Dummett and Foote. Have you read 12.1? Yeah. I think the theorem in 12.1 has more. I think it has divisibility built into the R's. I don't think you're wrong. Yeah. So examples like I was just saying, Z is a Z module rank 1, but the linearly independent set 2, it's not a basis. The treble above the span of 2 is not Z. 2 is a basis for 2Z, right, which is a submodule Z, but it cannot be extended to a basis for Z. So what's not native, so what I don't understand yet is this theorem. It seems to be saying something a little bit different. It's not starting with the basis 2Z. It's starting with the basis beta and then doing something funny to it to create a basis for the submodule. This example seems to be the other direction to me. We start with a basis for the submodule and then go, hey, you can't extend it to a basis for Z. But maybe I'm just, oh.
Yeah, I think the same for that example. You can take the basis 1,
Uh-huh.
Z, and then multiply that.
Oh, okay. Yeah, but like I said, it's not, I'm not saying this is wrong. I'm saying I don't have a good intuition for what this is yet. So I probably should prove it. Finally, a finitely generated module over PID is free if and only if it's torsion free. All right. And so then we move on to the big theorem. Any finitely generated module over a PID is the direct sum of a finitely generated free R module and a finitely generated torsion R module. So the direct sum of the free and the torsion. So the way to do this essentially is the following. You take the torsion piece to be the torsion of M, the set of elements with torsion, and also 0, right? This forms a submodule. Then you can take the quotient of M by the torsion. What's left is a free module, and that gives you this direct sum decomposition. That's about the only proof I'll do today. Okay, but of course, me saying that does not at all provide, well, the uniqueness, like I said, is unique, because I just said it's a set of torsion elements of M. That's not up for grabs. That's a unique thing. But the quotienting process doesn't have to give you a unique, it's like up to isomorphism, the quotient, yeah. Well, anyway, comment. If W1 through Wm is a basis for the free piece, then the direct sum of the cyclic submodules generated by the basis, this guy and that guy, with the torsion, that gives you a decomposition of the whole module into the direct sum. So this partly decomposes M into a direct sum of cyclic submodules, but we still have to study how the torsion rips apart itself into cyclic submodules. That's most of what we're talking about today. All right. So I'm going to keep following Roman here. And what Roman does at this point is he focuses attention on torsion. All right. Eventually, at the end of this PDF, I get back to stating theorems from Dummett and Foote, which merge these two ideas to state theorems for a finitely generated R module, which has both a free piece and a torsion piece. So what we're going to do is we're just going to study the torsion piece, understand how it decomposes a couple different ways, and then we'll put it back together with the free piece at the end. And then tomorrow and Friday, we'll study how this actually works out, hopefully for like the the V upper T module, and then hopefully, seeing the rational and canonical, rational Jordan form, the rational canonical form, and then hopefully the Jordan form, and how this stuff ties together. Actually, Friday might be how to classify abelian groups that are finitely generated with presentations. So suppose you define an abelian group by a set of, basically an abelian group is defined by a set of generators, right, that satisfy certain relations. And since it's a Z module, you can really look at an abelian group, finitely generated abelian group, as being the solution set of a set of homogeneous, equations over the integers. Then the question becomes, how do you actually understand which abelian group you're looking at? Because we're going to find our way to a theorem here, which says that every finitely generated abelian group is nothing more than the direct product of a copy of Z to some power, and then pieces with torsion, which are copies of Z mod this and that. Right? So how do you actually calculate that, given this set of generators and relations? I'll talk about that later this week. There's a pretty straightforward algorithm, which I'm sure has a connection to what we're doing today, but I'm not going to make that connection directly, most likely. All right? But, okay. I digress. Okay, so let P be a prime, and a P primary, or just primary module, is a module whose order is a power of P. All right. So this is the primary decomposition theorem. You have an M as a torsion module. You take the order of the whole module being the product of prime powers. This exists because we're working in a PID, which is a UFT, right? Technically speaking, there might be a U here, right? I mean, if you were just factoring, yeah.
So when I was reading this in the book, I was confused about how you get that that there exists a non-zero order. Because, like, for instance, if you take the direct sum of a bunch of Z mod P for all primes, and you just take the infinite direct sum of that.
Well, that would be outside our purview. We're talking about finitely generated.
Oh, because in the book it
our
says
modules.
At this point we can do some of this for modules that might not be finitely generated. Is this still here talking about finitely generated? Because if so,
well,
in the book it specifically said.
Yeah, I know. 12.1 Dumbfoot, he does mention that this primary decomposition theorem extends past the point of finitely generated, yeah. I think it's theorem 8 or whatever. But, yeah. Huh. So your question is it a restriction to say that the torsion has that kind of form?
It says, let this be blah, 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 and I'm like, are you saying that we can always find such a blah, or just consider only one?
Yeah, I don't know. I don't know what to say about that, Sam. It's a good question. Let me put that on my stack of things to ask my expert. I'm trying to burn it into my brain. All right, I think I put it in there. Ask me again next class. All right, where were we? So the point is, if that's the order, then what you can do is take the order and divide by the particular prime power. And so what's left is what? Everything, basically you're acting on everything except for that factor, right? And so in other words, what makes V and M be 0 in here? It's if V is in this, right? Because of course what happens when you multiply this, okay, so if good grief, if V is in here, right? That means V is already appearing as a product of everything in the order except for that factor. So when you hit it with that factor, then you've got everything in the order, but everything in the order acting together on anything in the module gives you 0 by definition of the order in the module. So this is a kind of sneaky game. You might recognize this game from the proof of the Chinese remainder theorem, where we do this thing where we take the product of the moduli and divide by specific moduli, and then do this calculation that's based on these slightly reduced moduli. This is the same kind of idea. It's not an accident that we need the Chinese remainder theorem to prove things later on in here. I digress. Anyway, this is the primary submodule of order that. And this is a decomposition of M into primary submodules. It's called the primary decomposition of M. I want to say, guys, that later on, when we contact the world of vector spaces over, a module, over the fx module built by linear transformation T, these are the generalized eigenspaces, actually. But anyway, I'm getting ahead of the story. Now, the primary decomposition is unique up to the order of the summands. So if you were to take a different set of primes, possibly non-associate, non-associate distinct primes. In other words, they're distinct and they're not associates of one another. They're genuinely distinct, not like 5 and minus 5. No, those are not allowed. Those are associate primes, but they're distinct. So non-associate distinct primes. Then it's the same stupid set of sets, right? And the number of them is equal. And by the way, the primes are equal up to associate after appropriate reindexing. And we can also say that 2R modules are isomorphic if their primary decomposition is the same. In other words, pairwise isomorphic. Yeah. So once you have that, he's like, well, that's nice, but I want to cut it more finely. Well, then what you can do is you can take these primary components and cut them down further. All right. And so this is the details of how we take a primary module and decompose it into a direct sum of cyclic modules. This decomposition is not unique. However, the set of annihilators is unique. So here we go. So this is a lemma, which he needs. So we have a PID over R, P prime. We look at PM equal to 0. What's that say? That says that P is an annihilator of M, or at least it divides one. Yeah? Then M is a vector space over the field. Remember, P is a prime, so that means that this is maximal, because prime is irreducible, and irreducible is mod maximal, that's a field. So that's a field. This is a vector space, and here's a scalar multiplication. And for any submodule S, the set S upper P, what's this mean? This is the set of vectors in S which is sent to 0 by P. Right? That's also a submodule of M. And furthermore, it plays nice with direct sums in the sense that if M is the direct sum of S and T, then the set of things sent to 0 by P and M is the direct sum of things sent to 0 by P and S and things sent to 0 by P and T. And you can pretty much see at least the sum part of it. That's like almost immediate. You can look at this and look at that and see why that's true. The intersection, why should the intersection of these two things be 0? That might require some thinking. All right. So from that lemma, we get the cyclic decomposition of a primary module. If M is a primary finitely generated torsion module over PID with order P to the power E, then we have that M is the direct sum of Langle V1 wrangle direct sum direct sum Langle Vn wrangle, where the annihilator of Langle V sub j wrangle close parenthesis. Oh, I forgot the open parenthesis, not start over. Open parenthesis Langle V sub j wrangle close parenthesis is equal to Langle P upper E sub j wrangle. I'm sorry, this is getting annoying. The point is that each one of these is actually the annihilator of each one of these is nothing more than the ideal generated by this prime power in the ring. And you can arrange these in ascending order such that that's a subset of Vn, which is to say, of course, that these powers, the exponents, are E. The top one is E, and then because if you annihilate something by P to the power E, right? If that sends it to 0, then p to any greater power also sends the thing to 0, right? So that's why p to the first, the lowest, the greatest power. I've got this backwards. Well, obviously I'm thinking about things upside down, but anyway. I should stand on my head. Unfortunately, it's not something I can do. Or I should just lay down. Like this maybe, I don't know. Or that way, I don't know. Let's see here. Let's see. So we've got a primary finitely generated torsion module. And the order is p to the e. So this is a kind of special case. There's just one prime, right? There's just one prime forming the order, and its power is e. This is kind of like the most sort of silly case. It's when there's just one p primary component. The whole thing is the p primary component with prime p. And so it says that you can rip it apart in this way, and not just that. If you ripped it apart in a similar way, then guess what? This decomposition and that decomposition, we have to have m equals to n, and the primes which form the annihilators of these have to likewise satisfy the same sort of condition, and which is also giving that. So in other words, these two chains of annihilators are identical in the sense that we could have different choice of u and v, but the annihilators will match up. The annihilators, again, are in the ring. Okay, so those are not like, you know. In other words, p and q are associates, and we have that fj is equal to ej. Those are the powers. Those are integers, yeah. And then finally, two p primary R modules are isomorphic if and only if their primary cyclic decomposition here match up. So we can test for isomorphism of p primary R modules by testing if they've got the same chain of annihilators. Yeah, in this sense. Then, of course, generally speaking, a finitely generated torsion module won't just have one prime, it'll have many, n of them, let's say. And so these are for distinct non-associate primes. All right, so any one of these would be like the theorem we just stated. Well, okay, so then m is uniquely up to the order of some n's decomposed into direct sum of these p primary components, where we can define m sub p sub j by this. That's the primary submodule with annihilator, that guy. And each one of these m sub p's can be written as a direct sum of cyclic submodules in the sense that the previous theorem stated. In particular, so we'd have like MP1 has this, cyclic decomposition, all the way to MPN has that cyclic decomposition, where the annihilator of Vij is equal to this guy. In other words, let's see here. So like if j equals 1, so if I equals 1 is fixed, right? See, I equals 1 is fixed. We have I equals to 1 all across this thing in brackets. And the j ranges from 1 all the way to k, k1 in this case. All of these guys are in the annihilator of this particular power of p to the I, p sub I. So p sub I to the eij annihilates this whole business in here. But let's see here. Vi1, this V11 is, let's see here. That would be annihilated by P1E11, right? Which is the first thing, the greatest, actually. So the highest power of the prime annihilates the first thing, down to this being the lowest power of the prime annihilating the last thing in this chain, the way it's set up. again, we have a uniqueness. And if you look at the proofs here, much of the lion's share of the effort spent on proving uniqueness, if you look at it, like that's the part that stings, from what I see. But you can prove that if you had another such decomposition, breaking apart each Q sub j primary component into a direct sum of cyclic submodules there, then after appropriate reindexing, the number of summands is the same. You get the same number of distinct prime factors, and the chains for each prime factor have to match up. That's the uniqueness. And furthermore, if you can take two torsion finitely generated R modules, finitely generated, there you go. That was up here, wasn't it? Finitely generated. That's in Roman, which, of course, shame on you for not reading. But, sorry. Anyway, I'm not being nice. I should actually scan Roman for you guys. I'm sorry. But anyway, if you have that two different decompositions like so, and you can match them up with the same prime structure up to associate and the same number of pieces and arranged pieces for each of the P primary or Q primary components. In other words, if the annihilator chains match up for each of the components, there's no stupid in there. Sorry, that's just me. Frustrated, there's a lot of things to say today. I'll get over it. Then you have the two torsion, finitely generated torsion modules are isomorphic. And of course, that's not enough. We can't stop there. No, of course we could not stop there. No. Far be it from us to stop there. We then have so that was the primary cyclic decomposition. Now we talk about the elementary divisor decomposition. And so this chain of annihilators, right, is unique except for the order. The multi-set of generators, Pi upper Eij, is uniquely determined up to associate. You can have repeats in this, right? See, because each P primary component can have multiple copies of the prime. Like you might have in your chain, you could have like 3 squared, you could have another 3 squared, you could have a 3, you could have a couple 3 to the power 5s in there. And you'd have to keep track of all of these because each one of these would make a part of your chain for the prime 3. And you don't combine them. So we're talking about as a multiset where we keep duplicate elements. That's what a multiset is. Multiset is what you think set is before people tell you it's not. Right? We try to unlearn that you should keep 2 apples. People say that you have a set with 2 apples and a banana. How many things are in the set? And then you're supposed to say, well, we only keep 1 of each element, so there's 2 things in the set. But you know that there's really 3 things in the set because you actually think about sets in terms of multi-sets. Well, good for you. Uh-oh. 2 apples are not equal. Oh, wow. These are apples in the sense of elementary particle physics, indistinguishable, fundamental apples. Apples in the principle of things, like electrons. Dang it! They're 2 photons occupying the same... No. Yeah, all right, fine. No, I will not focus. All right, so the generators, these guys, are the elementary divisors of M. So the elementary divisors of M are the set of annihilators for the cyclic submodules in the primary decomposition. There's a really slick sentence in Dummett and Foote where he connects the invariant factor decomposition to the elementary divisor decomposition. We haven't said the invariant factor decomposition yet, but there's like a line and a half where he connects the 2 concepts. It's very. I wish I gotta find it, but anyway. But that sentence won't help you do calculations. I have gory examples at the end of this PDF, which we will get to. So anyway, the theorem is that if R is a PID in the multiset of elementary divisors, it's a complete invariant for isomorphism of finitely generated torsion R modules, which is to say that M and N are isomorphic if and only if they have the same set of elementary divisors. Multiset of elementary divisors. remember, that makes sense. Even if M is chickens and N is scorpions, if they're both Z modules, you can compare their elementary divisors because elementary divisors are in the ring. And if chickens and scorpions share the same base ring, then you can compare their elementary divisors, right? Just saying. So here, the direct sum of primary cyclic decompositions is once more a primary cyclic decomposition. Indeed, if we had, by the way, the direct sum of A and B, then the elementary divisors of M are the multiset union of the elementary divisors of A and the elementary divisors of B. And you can really just see that, because saying that you have an elementary divisor decomposition of A and B is to say that it's like broken up into a direct sum of these cyclic submodules. So you just look at it. You've got a list of cyclic submodules, each with an annihilator of p sub upper, p sub I, e to the whatever power. That may or may not make sense to you yet. Maybe this will help. If S and T are cyclic submodules relatively prime order, then the direct sum of S and T is cyclic, with the order being the product. Well, so the point is, we can keep track of the order of a direct sum as long as we collect relatively prime orders. Yeah. So there's some way of reformulating a direct sum like this as long as we keep track of, let's say the decomposition should be unique as long as we play this game where we're keeping track of relatively prime things. Let me put it in more specific terms. So we do this handy-dandy elementary divisor decomposition to collect, let's see here how to do it. We collect all the, we can combine cyclic summands with relatively prime orders, actually. So we can take the different p primary components and mix them together. We can mix them together if we're strategic to take copies of just one prime of each summand, right? You can build products of the primes such that, and then build a product, take something from here and something from the middle and something from there, and then take something and then take another. That's your first thing. And then your second thing, take something from here and something from the middle, something from there. That's your second thing. Those two things will be relatively prime because they're built well, will those be relatively prime? They will not be relatively prime, but they will have a divisibility condition, actually, if you do it in the right way. I can't describe this with words. Here we go. So what he says is you pick off the leftmost submodule from each group. So like V11 all the way out to VN1, that's your D1. And then pick off the second one from each group, right? It could be that these are 0. So we just would direct sum with 0, it just basically disappears. And then all the way out until one of these has longest length, yeah? So that, one of these has got m of them in it. So, yes. So at least one of these has m in it, and so it could be that the mth one, there's only one. It could be that this has gone away, everything up to it's gone away. Only this one is long enough to pick up this in a non-trivial sense. Okay. Anyway, I think this is hard to see without it. I really need to look at an example. I don't. All right. Well, here's an example, sort of. So suppose you had, this was your primary decomposition with cyclic subdivisions, so to speak. So you got like prime 1, prime 2, prime 3, right? And this one over here, so D1, I pick off this and that and that. That's my D1. My D2, I pick off this one and that one. That's my D2. When I get to 3, this has only got 2, so 0. It's only got 1, 0. This is the only one that matters, so it gives me 3. So by doing this, rearranging them, you have the same, like if you look at this, you've got the same set of elementary divisors. They've just been sort of rearranged, right? And they've been rearranged in such a way that the order of this and the order of that and the order of that satisfy this divisibility condition. In particular, the order of D3 divides the order of D2, divides the order of D1, like so. This is the so-called invariant factor decomposition. All right, so the same example, let me make it a little bit smaller. So if you look at what we had to start with, we had, I need to get it on the same stupid page, unfortunately. Right now you can see it, I hope. All right, so look at this. Where is this P1 cubed, P1 squared, P2? That's this. I mean, these are the annihilators of those guys by construction. By definition of the P prime, by the P cyclic decomposition. These have to come from those, the annihilators being those powers of the prime 1. What? I'm sorry, the prime. Dang it. Oh. I'm sorry. I've gotten confused about the connection between this and that. This is clear. Let me focus on that. My mind is not clear to make the connection with the original M. It could be done. It's not that big a deal, but let's just move on since I have more fruitful things to say here in the remaining couple minutes. So the point is, you've got 3 primes in play here from the 3 primary components. Prime 1, I've got, so I pick off the top power of prime 1, which is the cube, the top power of the prime squared, which is P2, which is just P2, the top power of P3, which happens to be P3 cubed. All right. Then D2, I look at it and I go, okay, well, I've got no, P2 is only, there's only one P2 to pick because the second one only had one factor. There's still another P1 to pick. In fact, the P1 I picked was P1 squared. And then P3, there's another P3 cubed, actually. There's 2 of them. So I pick that up. And then finally, by the time I get to the third, I just pick up P3. Right. So for a given prime P, the elementary divisors need not include P itself. So the elementary divisors, like I have P1 cubed, P1 squared, and you can have repeats like P3 cubed, P3 cubed. This is, so when we look at linear transformations in the decomposition, like Jordan form, you've already seen this kind of behavior. This is something akin to like you could have 2 Jordan 2 blocks, but you don't have to have even 1 Jordan 1 block. That's the phenomena we're seeing here at the level of the general theory. Anyway, this leads us to the invariant factor decomposition, which says that M can be broken apart. Any finitely generated torsion module can be written as a direct sum of these cyclic submodules with orders which satisfy this divisibility condition. And this is called the invariant factor decomposition of M. The D sub i's are the invariant factors. The multiset of invariant factors is uniquely determined up to associative M. The multiset of invariant factors is a complete invariant for isomorphism. By the way, the annihilators of the invariant factors are called invariant ideals. So D1 is actually an order of M, because D1 annihilates all of M, if you look at it, right? Because if you have this divisibility condition, so it says the order of every piece divides D1, right? I mean, look at this. These are orders for each one of these pieces. And so if D1, if all of these divide D1, that says that this D1 will kill everything in every summand. And hence it's an order for all of M. In other words, dm is the annihilator of M itself. That's what we should expect. It would be the minimal polynomial in the context I'm most interested. So the following are equivalent. M is cyclic. This is a special case. If we have a finitely generated torsion module with order this, then the following are equivalent. M is cyclic. M is the direct sum of these, of order PE to the I, PIEI, and the elementary divisors of M are prime power factors of mu. Are the prime power factors of mu. Let's see here. Anyway, I'm going to move ahead here. Because I actually had an example. I'd like to show you an example. So these are the advertised corresponding theorems in Dummett and Foote. So the main difference is that Dummett and Foote does not assume that the whole module is torsion. So there's a free piece. See, there's R to the R, and then you've got these pieces. They satisfy the divisibility conditions. So Dummett and Foote starts with the invariant factor form. See the opposite? I mean, so Roman started with the elementary divisor form, and from that he derived the invariant factor form. Dummett and Foote kind of does the opposite way around. So of course R is the so-called free rank, and then we have the corresponding fundamental theorem in elementary divisor form. You can, again, the free part and then the torsion part, but the elementary divisor form organizes the torsion piece differently, right? So the prime powers in here are the so-called elementary divisor. There's no divisibility condition built in here, right? I mean, you could say certain divisibility conditions as they relate to various powers of certain primes, but there's no like overarching D1 is divisible by D2, which is divisible by D3, you know? And then, of course, there's the primary decomposition theorem, kind of working our way backwards, finally. And I just want to show you this example, and then we'll stop for today. So here is the application or the exposition of this theorem, these theorems that we've been looking at, as they relate to abelian groups of order 1800. So, by the way, if an abelian group is finite, it is finitely generated, because you can just take the whole group as a set of generators, and then it's finitely generated because it's a finite group. So this is definitely finitely generated. What's possible? Well, you can either look at it from the elementary divisor, or you can look at it from the invariant factor form. 1800 factors into 2 cubed, 3 squared, 5 squared, times 5 squared. So your primes are 2, 3, and 5. And the question is, how do you arrange them? Elementary divisor form, here's the elementary divisor form. So we got like 8, 9, 25, 8, 9, 5, 5, 8, 3, 3, 25, 8, 3, 3, 5, 5, 4, 2, 9, 25, 4, 2, 9, 5, 5, 4, 2, 3, 3, 25, 4, 2, 3, 3, 5, 5, 2, 2, 2, 9, 25, 2, 2, 2, 3, 3, 25. I was supposed to write this one first. I lost track. So this is the list stolen from, by the way, so Dummett and Foote talks about, you know, what is this? This is the fundamental theorem of finitely generated abelian groups, which is back in his group theory section. You should go read that now. It will make the theorems in section 12.1 come to life. The one thing 12.1 is missing is examples. And the reason for that is pretty simple. He's given you examples earlier in the book. In fact, they've given you techniques and strategies for how to rip apart this and get to that, sort of algorithmically even. Like, there's tons in that section about how to understand these two different worlds. Excuse me. And what they mean for you. Anyway, here's all of the elementary divisor forms possible, the way you could arrange 3 copies of 2, 2 copies of 3, and 2 copies of 5. This is all the different distinct elementary divisor rearrangements right here. These are the corresponding invariant factor form. So you take basically 1 copy of the prime 2 to a power, 1 copy of the prime. So basically you've got a 2 cubed, a 3 squared, and a 5 squared. You only have 1 from each list, so you pick all of them, put them together, you have a single invariant divisor, 1800. This one here, you pick an 8, you pick a 9, you pick a 5. That's your first invariant divisor, that's 360. You're left over with a 5, so you got a 5 left over. Here, you pick an 8, You pick a 3. You pick a 25. That gives you this, I can't read my writing, 600 and a 3 left over, right? Right here, look at this. You pick an 8. You pick a 3. You pick a 5. 8 times 3 is 24 times 5 is 120. Then the next one, you're left with this 3 and left with this 5. That gives you the 15. Next one here, we pick a 4. We pick a 9. We pick a 25. That gives us the 900. You're left with this extra copy of Z2 for the next invariant factor. You pick a 4. You pick a 9. You pick a 5. Leaves you the 2 and the 5. You pick a 4. You pick a 3. You pick a 25. That gives us 300. You're left with the 2 and the 3. You get the idea. So this is... Now, if you think about it, there are other ways you could, I mean, if you think back to last semester, there are other ways you could arrange these things, right? There are other direct products of copies of Z that we could form isomorphisms to, but those just wouldn't fit in this, either one of these standard nomenclatures, right? Like I have, neither of these is really the P primary components, right? Like we could, well, I guess P primary components is really just a matter of putting parentheses on this side. Right? Like P primary component for 2, P primary component for 3, P primary component for 5. But anyway, I should stop because we're way over time. So, sorry guys. I will shut up.